So we move into this chapter, and this is chapter number 4. And what is the title of chapter number 4? Force system resultants. Maybe this is the worst title of a chapter that I've seen in any textbook. Have you browsed through chapter 4? What's one of the main themes of chapter 4? Moments. The first half is moments of forces. And then you can have a moment of one force, then you have multiple forces, so you then have moments of each individual force. And then just like vectors, you can sum force vectors, you can sum moments because we represent moments as a vector. And so that's the first half. But then later, as we get through the textbook, they talk about distributed systems, distributed loadings, equivalent systems, and so maybe that's why this title of this chapter is so obscure in my opinion. It's force system resultants. It doesn't mean a lot to me. It doesn't touch me like, oh, that's exactly what we're studying. I think it would have been better if they would have just maybe busted it into 2 chapters and the first chapter just deal with moments. But that's okay. Let's press forward. So we start with individual work, so I don't want you to talk to your neighbor on this clicker question. It's multiple choice, and a mailbox sits on a horizontal post, or horizontal wooden support. Right here it is. And it's attached to a vertical wooden beam or post that's sunk into the ground. And it's pinned right there in between. And on one end, the long end of the vertical beam, not the vertical beam, on the horizontal beam, you put a mailbox, and the mailbox is heavy. And in which location will chain or chains help support the mailbox? Will it be only in A, right here, or only in B, only in C, or A and C, or B and C? There you go. Okay, so this is what the class believes, that to support this, it's only at A is going to help. All right, now, what will the mailbox want to do? The heavy mailbox will want that horizontal support to rotate which way, and it'll rotate around this pinned connection right here in the middle. Even if you put a couple nails there or something, it's still going to want to rotate around that point, even without any chains. So if it starts to rotate around that point, if you look at the distance between this point and this point, for chain B, it would be brought closer together if it moved in that way. Wouldn't these 2 points come closer together? And so basically you can't push a chain, you can only pull a chain, or you can't push a rope, you can only pull a rope. It can only be in tension. The chain cannot be in compression. But if I look at this point and this point for chain A, they would come apart. They would be elongated. The chain would be elongated. It would be in tension. And yes, it would support it. So this is good. This would do no good at all to help support it. How about C? Same thing. You look at it and you say, well, if it did actually move down, mailbox move down, rotating around this point, then chain C would need to be able to support compression. Chains can't support compression. It's not going to be any good. So you say that only in the location A is a good place for the chain. So very good. Let's take a look. And looks like everybody had that one figured out already, right? That's good, because this is really a lead-in to this chapter. Here's another question. Individual work first, and then we will do it with follow-up teamwork. We have a mass, a beam balance, and there's a mass on this end, and that's 10 kilograms, and the mass at this end, which is unknown. What does the mass on the right-hand side need to be for this system to be balanced? I change it into a numeric, and we'll go ahead and get started. So let's take a look at our results. So the vast majority said it needs to be 5 pounds or 5 kilograms. Why does it need to be 5 kilograms in order to have this system balanced? There's a longer arm or lever or whatever, right? And so what you're looking at, you're saying this is the point at which it's going to rotate, possibly rotate. So this is the right answer, 5. So let's see how we did before. Oh, a lot better. We've improved. True? All right. All right. What happens when a force is applied to an object? Before, it makes it want to translate, but it has a tendency also to possibly to make it want to rotate. And so now it's a different type of motion. And the moment of a force, or simply called the moment, sometimes you drop of the force, is the tendency for that force on an object to make that want to rotate about a particular point of interest. Okay, and so you would say that this is our symbol, M, for the moment of a force. It is subscripted. There is a letter O. Okay, so we're saying around maybe the origin, but we could talk about the moment around point A, or the moment around point B, or the moment around point C, etc. But it's often the moment around point O, and it's the product of the magnitude of the force and D. Okay, so that's what F is. It's the magnitude of the force. So, and D, so this would be typically newtons or pounds, and D, what do you think it is? It's a distance. And if I'm going to measure distance in SI, what am I going to use? Meters. So we're going to be looking at this moment of a force, which has units of Newton meter, the product of a Newton times a meter, and it's given by the equation F times D. And D is the moment arm. And that moment arm is it's the difficult part of this whole equation. It's that shortest distance from that point to the force's line of action passing through the point of application of the force on the object. So if I have an object, and I have here is a point O, right at that point O, and I have a force here, F, and it's applied at this point right there on the object, I introduce the line of action that's continuous. It's a line that goes on forever and ever, right? And the shortest distance from this point O is going to be here to here. It's not going to be here to here, or here to here, or here to here. All of those are connecting O to the line of action. But one of those lines is the shortest line, and it's characterized by being what to the line of action? Perpendicular to it. And so that's our moment arm D, that distance, the shortest distance. That's easy to show in 2D. We'll solve a bunch of problems in 2D before we get to 3D. So there's a long definition of what D is, moment arm. If you go back to here, what was that moment arm? 2 meters. Because the weight is acting down. That's our force, our weight. And then over here, weight's acting down. What's that moment arm? 1 meter for this side. This side makes it want to rotate counterclockwise. This one clockwise. When they're balanced, the sum of those have 0 moment from that 2-force system on our balance beam. Consider a box. It's a simple object. Here it is. It's colored. It goes from 0, the origin, out to 2 in the x. It goes from 0 to 2 in the y. All right, it's just a box, 2D problem. There's a force applied. Where is it applied? It's applied on the top edge of the box, right in the middle of that top edge. And so at this location, if I said, what is that point of application or where that force is applied, it would be at the x location 1 and the y location 2. True? Okay. And its magnitude is 250 newtons, and its orientation is characterized by this angle of 30 degrees. point O needs to be defined. We're trying to calculate the moment of that force around a particular point. Well, often point O is right at the origin. Okay. And it's at the lower left corner of the box. So the question is, can you calculate the moment arm for that force F about point O? Can you calculate the moment arm for that force F? How would you calculate it? Nope. We want a distance d first, and then you're going to get to the method of moments later. There's 3 ways we're going to calculate the moment of this force. But the first is to get the moment arm distance d. I'm sorry? No, it's not. I don't think it's the square root of 5. It's not going to be a trivial little one equation. Oh, I can see it. Here it is. You're going to have to work to get it. How would you work to get it? Okay, well, let's do this. What did I just draw right here? It's the line that represents that line of action of the force, and it goes through the point at which that force was applied to the object. Now, this is a line that's parallel, but does it go through the point of... No, it doesn't. So we need to get that particular blue line, right? And now, what's the minimum distance? Is this d? Is that my moment arm? No. I have to come over here, and that's a right angle. That is, that's a 90-degree perpendicular, so it's 90 degrees right there, right? And so if I want to find d, how would I go about finding d? What is your favorite triangle for this semester in this class? The right triangle. So you look to make a right triangle. Somebody says, I think going from point O to this point, and then out to this point, and then back to there. Yeah, you could do a right triangle that way, true. Or don't go on to the top side of D, go to the other side of D. There's a right triangle as well. True. Your choice, which one to work with. Okay, so if we focus on this top triangle right here, let's introduce a letter for the length of this distance right here. Let's call it either A, B, C, or H. Why would you call it H? Because it's the hypotenuse of a right triangle, isn't it? All right, can you give me the distance H? Just from the information given in the problem. Square root of 1 squared plus 2 squared square root of 5. So that's the distance between the point of application and O, but we want the moment arm, which is D. So what is D now in terms of that? All right, I'm going to pause, walk around, and let you do it, because you've got to be able to do these type of problems quickly. Right? So you had that distance. That's what you had. How about if I give you a hint? You guys, I got a lot to cover. Please help me go faster, because otherwise I'll just default. That's why a lot of faculty just talk to themselves. It's like, consider this triangle first. You need to consider that triangle as well as this other triangle. That's a right triangle too, isn't it? What will really help you with that triangle? Either get this angle or that angle. I would say, to me, my mind works to get this angle. Is that a help? Because I could then get this angle. All right, let me leave you with that hint. All right, did some people calculate this angle right here? What did they get for this angle right here? 63.43 degrees, right? Now, if I told you, you got that by arctan of opposite over adjacent, true? Now, can you use that to get theta? All right. Somebody already got it? What did they get for theta? 56.565. I'm keeping all the digits. 56.6 degrees, true? Well, you have a teammate right there. How do you get it? No idea. Okay, let me pick it up here. So I think a lot of you have it figured out now. So then once you have this 56.565, and yes, please keep all those extra digits during intermediate calculations. Then you would focus back again on this right triangle. You know the hypotenuse that we calculated before. So this distance d is the hypotenuse times the sine of the 56.565 degrees. So d comes in at 1.8660 blah, blah, blah. Or round off to d is equal to 1.87 meter. That are units for distance. I don't think I actually claimed that they were in meters, but all of these are in meters. If this force is in newtons, that's what makes sense, okay? Then once you did a lot of work, but you have that moment arm, what do you think the last part of the question is? Multiply. Now multiply and calculate the moment of that force about the point O. Well, that's why we went from O is the point for the moment arm out to that line of action. So the moment of that force is 467 units Newton meter. Look good? There's two other ways we're going to solve this problem. One is using cross product. Somebody, I want to use cross product. Well, maybe I say you must calculate the moment arm. That's fair game on this question, on the exam. And then another time I say, no, don't use the moment arm. Calculate it using the cross product. And then the other is principle of moments, which we'll get to. And somebody else, I think you said, oh, I want to do it this way. Well, you're describing the principle of moments. So let's get all of these in one lecture, okay? So let's press forward. All right, this is individual work, clicker question. So multiple choice. Consider 3 points A, B, and C. Where is point A? Where is point B? And where is point C? And we want to talk about the magnitude of the moment that this force exerts on the object if you're calculating the magnitude of the moment about either point A, is that the greatest of the three? Or point B, or point C. So in other words, the magnitude of that force about point A, magnitude about point B, magnitude about, or are all of them give the same magnitude of the moment about either of those points, A, B, or C. Hopefully you understand the question. Let's start the time. All right, everybody's in. So we want to say we're going to calculate the magnitude of the moment around any point, and that would be using the equation where m is equal to F times d. True? And so I'd say, does this line of action passing through the point of application of this force, does it change for any of those moment calculations? No. But if I said, what is that d for point A? I'd say, oh, we just did that. That's the d for point A. And so he says, what's the d for point? Is this the d for point B? No. What is it? Looks like this. The d for point B. How about the d for point C? Is that it? The d for point C? And now we want to compare. So the d, the moment for A doesn't change to F. It's the d of A. And then this, likewise, the moment that the force generates, the moment of that force around point B would be the same magnitude of F times d sub B, and the moment about point C is F d sub C. Again, I'm just emphasizing, are all of these the same in the equation? Yes. Now, the question is, are all the d's the same? No. Can I re-ask that question, and you can work in teams? All right, everybody's in. I'm going to go ahead and zero out the time. Everybody's in. So let's take a look. Well, after some discussion, the class is 100% correct. True? But before the discussion, well, there was some benefit to the discussion. Now, when we get to cross product, sometimes it's really hard to see, what is the mathematical relationship, how things, which one's larger, which one's smaller, or even when we decompose. But with the moment arm, you can often see, oh yeah, that creates a larger moment. Here, let me ask another question. What happens if I introduce the point D, and the point D is right there where F is applied to my object? What is the moment of that force around point D? Not a clicker question, but what is it? It's zero. It's zero, isn't it? Now, somebody says, let's move D over here. All right. Well, wouldn't this be the moment arm distance? I would have to get D for that point, distance for point D, right? Somebody says, let's put D right there. And then I'd get the moment arm distance. And the way I've tried to sketch them, if this length of this line is precisely the same as the length of that line, but there's something, let me not call it D and D, let me call it point D and point E. There's something different. Even if they have the same length of the line, point D and point E have the same moment arm distance, there's something different about point D and point E. What is the difference? Which way it wants to rotate. So that force around this point D will make it want to rotate in the what direction? How would I describe that direction? Counterclockwise. And around point E, it would want to make the object rotate clockwise. And now we got to pick a positive and a negative sense of direction. All right. Which one did the book? Maybe you read the book, right? Which one did the book say, look, for the whole book, let's just pick this one as being our positive sense of rotation for our object? Counterclockwise. It's the counterclockwise. So this is our positive sense, and this is our negative sense. So one thing that this equation doesn't give us, which the cross product will give us the plus or minus direction, the sign. This one, you have to always use your right-hand rule and determine that sign so that you could say, oh, it's going to be rotating in the positive counterclockwise direction or the negative clockwise direction. Okay? All right. All right. Consider point, this is individual work. Consider 3 points. Here's point A. Here's point B. Here's point C. But we have a different force. It's 250 newtons, and it's shown to be a vector just in that orientation right there. It's applied to this object. Compare the magnitudes of the moment of the force. Is it greatest when it's about point A, B, C, or the same for points A, B, and C? Multiple choice, individual work, 30 seconds. All right, so you say there is something different. Here is the point of application. Maybe we label that D, right? But is it the distance from the point of application to C, and then the point of application to B, and then the point of application to A? Is that what's critically, and maybe these distances, this distance going to A is larger than the distance going to C? Is it? No, none of that. It's the line of application going through the point of application, right? Of the F. And then you would say, what's the moment arm distance, the minimum? That would be that distance for going to C. It would be that distance for going to B. It would be that distance for going to A. And what about these moment arm distances? They are the same, so this is the case where most of us were on top, right? It's the same. All right, let's press forward. All right, how would we calculate? Maybe in the interest of time, I sketch this out and don't do it numerically. How would you calculate the moment arm for this force, as shown, around this point, as shown? How would I calculate that moment arm? Should I just talk through it? All right, let's just talk through it. There's the point of application of the force on my object. I've got to get, then I put a line that's the line of application of that force, and it goes all over. I mean, long line, right? And then I focus on that point A. That's where I'm getting the moment about, that point A. And then I make a sketch, and I say, well, looks like this would be a good representation. And I need the length of that line. That's what my moment arm distance is. All right. I better be good at right triangles. Okay. I can then draw this line from here to here, true? And that's a good right triangle. And this is that side D. And either I focus on getting this angle or that angle, but I've got to work on getting one of those angles. And then I could use my information from right triangles to solve for that length of this side D. True? Well, let me just say I'm going to focus on getting theta. All right. If I could get theta, I also, h isn't too hard to get, is it? Can you see what h would be? It would be the square root of 3 squared plus 2.3 squared. Yeah, so basically I looked at this right triangle, which has the same hypotenuse side, to get h. True? Okay. All right. Now, how am I going to calculate this angle theta? How am I going to get that angle theta? Well, a lot of times I'll work and I'll say, well, this is all 180 degrees. True? There's 90 of it right there. Could I get this angle phi right there? Because then I would have 180 is equal to 30 plus 90 plus phi plus theta. If I'm looking for theta, if I could get phi, then I got theta, right? And so what is phi? Yeah, arctan. Once you solved a few of these problems, arctan of 2.3 divided by 3.0. Is that true? Good. Then we get phi. Once you got phi, then you get theta. Once you get theta, then d is equal to h times sine of theta. True? A lot of work to get that moment arm. Sometimes there's a lot of work to get that moment arm distance. Okay, which way would this force make it want to rotate around point A? In the positive or negative sense of rotation? In the positive counterclockwise? It would be, that's right. And so then we would calculate the moments equal to the 350 times d. Units would be Newton meter, and you could say it's going to want to rotate counterclockwise or put a positive on it. Sometimes the book will put, let's say this moment around point A would be negative 50 Newton meter, and this is the positive sense of rotation, which means it's because of that negative sign, it's in the opposite. Okay, for this problem, D comes in to be 1.44807 meters, and then the moment is 506.8 Newton meter positive in the counterclockwise direction. So put D is equal to, there you go. So that's fast. You're all fast to do that. Okay, let's press forward. Now they can do it very mathematically, and it would use the cross product. So this section is just a review of just math before we learn that the cross product is R cross, gives the moment is R cross F. So somebody says, here's a vector A and a vector B. Can you perform the operation of just getting the cross product of A and B? Well, the resultant is a new vector C. And you can talk about the magnitude of C from memory. What is the magnitude of C? The magnitude of A times the magnitude of B times what? Sine of the angle in between them. And you know what? That looks a lot like the dot product, doesn't it? But it was the cosine. But we get both the magnitude as well as the direction. We get a vector resultant. Did the dot product give us a vector resultant? No, a scalar resultant. Okay, so how do you get the direction now if I got the magnitude of C? What's the direction? What's it related to? It's perpendicular to both A and B. That's the key idea. So C is perpendicular to A and perpendicular to B. So you think about taking two vectors. Here's vector A and vector B. All right. First of all, join their bases together. If you put their bases together, here's A and here's B. Then what does AB sweep? You can think of it kind of like gets you 3 points. It gets a plane. It gets a plane. A two-dimensional. In 3D, it gets a plane. Then if C has to be perpendicular to A and perpendicular to B, then what you have is it comes perpendicular to that plane. Maybe you show it as being perpendicular to A. That's hard to do, to show it also perpendicular to B. That's what C is. That's how you get the direction of it. Now what we do is we decompose or express A as a sub xi plus a sub yj plus a sub zk. Isn't that our standard Cartesian vector form? And then what is vector B? Well, isn't it b sub xi? What does this bx mean? What's this ax? It's just whatever the magnitude of that component is in the I, and then magnitude of the component in the j and the k. So this is b sub yj and then b sub zk. True? That's general representation of vector A, B, and C. And then if you did the A cross B, what you do is you can spell it all out where you take this component and you cross it with everything, and then this component cross it with everything, and this component cross it with everything, right? And you get a very long equation. This is done in definitely in your math classes, your physics classes. If you haven't seen a cross product before getting the statics, something's wrong with your education. All right, so this is the review. And then you go through this, you say, let's say when I do the I cross the J, when I just do this component, well then I really have the magnitude AX times the magnitude BY, but I have this I cross J. What is that? Use the right-hand rule. In the I direction, curl the fingers to the J. Where's the thumb pointing? K. And you need to play that, and you need to go, okay, then I'm going to do I cross K. Then I'm going to do J cross I and J cross K. And oh, by the way, I should have put in I cross I. And then I should put in J cross J. And all you have to do is work out 9 of these. K cross I, K cross J, K cross K. And that really gives you the formula. So who wants to help me here? Somebody, you in the front team, of the 4 people right here, what is I cross I? I cross I. Well, you would go back and say, what's the angle between I and I? 0. Sine of 0 is 0, 0. All right. And then we just talked about using the right-hand rule to get I cross J. So maybe you think about, here's our traditional I direction, our traditional J direction, traditional K direction. All right, so this one I gave. How about this one? First row over here. I cross K. You just take the little vector I, you cross it into the k, use your right-hand rule, and what is the resultant of I cross k? Only these four participate. What? He's almost there. Keep going. Negative j. Is there a difference between positive j and negative j? There is. All right. All right. Next row back. 3 people. What is j cross I? Negative k. Very good. All right. Over here, 2 people. Let's do j cross k. Use your right hand. J cross k is positive I. Perfect. Positive I. All right, right behind them, those 3. What is j cross j? J cross j. 0. Very good. All right, this 3 in the front, the talkative team. No, you guys need to talk more. Okay, k cross I. J, positive j. That's right. All right, over here we have k cross j. K cross j is negative I. You're right. And then the rest of them in the back. K cross k, 0. That's exactly right. So once you figure that out, then you can work it out. But you know, how do we remember the formula? We use a little memory enhancing tool. We just say we'll construct this 3 by 3 and then calculate the determinant of it. But it's really not a 3 by 3 of a good matrix. It's a 3 by 3 of a funny matrix that helps us remember how to calculate it. And so what do? You remember that if you wanted to calculate the cross product, A cross B, you're going to get a resultant C. I would say C is, you can calculate by remembering to construct this matrix I, J, K. Those are the unit vectors on the first row. Then you put the components AX, AY, AZ on the second row, and then BX, BY, BZ. How many people have done this before? How many people have not done this before? All right, we're ready then to do this exercise. Let me just remind you very quickly. You get a 2 by 2 on the I minus a 2 by 2 on the J plus a 2 by 2 on the K if I expand that determinant. And basically for the I, you're going to cross this, and you're left with the 2 by 2 is AY, AZ, BY, BZ. Did I jog your memory correctly? Is that right? Or did I make an error? All right, and so this is our C. And then how about for the J? Don't forget this minus sign, right? And then you cross, and then what you're left with is an AX, AZ, BX, BZ. And then for the K, you cross, you're left with an AX, AY, BX, BY, and this is a plus. True? You ready? Given A is this vector and B is that vector, compute A cross B. All right, so hopefully everybody was able to get that C, which is A cross B, is going to be, what, negative 5 in the I, and then you have plus 20 in the J, and minus 10 in the K. So in interest of time, I'm going to press forward. Got it? All right. A cross B is the same as B cross A. True or false? Yeah, everybody got that one, which is good. So it's not the same. They're different, aren't they? So the magnitude of A cross B, is that the same as the magnitude of B cross A? All right. So the magnitudes are the same. It's the direction which is the change. True? Yeah, it's the direction that's the change. So let's press forward. So now once we've reviewed the math of the cross product, we find that we can use it in engineering by knowing that the moment of a force, you can derive or establish a vector formulation which gives us that the moment of that force is R cross F. Now, that raises a good question. What exactly is R and what exactly is F? Well, F is pretty easy. Isn't it the force that's applied to my object? So that's our force. Okay, that's our force vector. We've been working with force vectors a lot already this semester. Now, R. What is R? It's a displacement vector. It has to be a vector. It's a displacement vector. And it begins and goes from where and goes to where? Goes from the point O. So if I wanted to calculate m sub A, it would be R from point A to some force. Now this is where it gets a little interesting. So if I had, let me do this one. Here's my object here. Here's my point. Let's call it O. Here is my force. I'm going to put it right here on my object, right there, applied at that point. I then talk about the line of application that goes through that point, right? Okay. Is R only the point from O to the shortest distance right there? Or could R be to this point? Or could R be to that? First of all, those are different R's, aren't they? They're not the same R. So it's something special. This is the complicated. What about that R? First of all, if I do the cross product for any of these R's as shown, you will get exactly the same answer. Because there's only one answer for the moment of that force around the point O. The moment of that force around point O is some R cross F. F isn't changing. This isn't changing. But all of these R's work, but it's not going to change the final answer. That's a mathematical magic. Okay? So R is from point O to anywhere along the line of application of F. What often is the most convenient point to take it to? The point of application of F on our object. But that is just often the most convenient point to take it to. You could take it to this point, that point, any other point. It would give you the same answer. Now, this brings up the great principle of transmissibility, meaning that here is my force F. If somebody says it needs to be applied at this point, let's call it D on the object. Somebody says, no, this is the same F, and it's now applied at point E of the object, or the same F applied at point G of the object. See, I'm changing the point of application, where it's applied to the object. Will these give me different moments around point O? It's the same F in all points, but it's a different point of application on my object. They give you the same answer. They'll give you the same moment. Meaning that the force is transmissible along its line of action. So you may move it conceptually to a more convenient spot in order to do a moment calculation, to do it even with the cross product. All right? All right. Okay, this is individual work here. The vector cross product can be used to compute the moment. Here it is, moment of a force about point O. When this is R and that's F, the vector R is, and I get to give you a multiple choice. Is it from O to the beginning point of the vector F, O to the ending point of vector F, O to the point of application of F on the body, or from O to any point on the line of application of F? Yeah, this is the one that's often used but it's not what really R is defined as. That's the definition. The best answer is D, isn't it? That's what I was trying to say in words over and over again. Okay? That's the real definition of that R. All right, calculate the moment of the force about point A using the cross product. Is this the same problem?
Yes.
It's the same problem. Well, okay, instead of using the moment arm distance, how would we calculate? Well, we would first of all get a vector R. That's going to be the hard part. And then we would get vector F. No, here's A right there. So you can set A as the origin if you like and put your little coordinate system down here. That'd be fine. Put X and Y right there. You can do that. But what you really need is R. All right, so R is the displacement vector. Okay, what is the displacement in I and what is displacement in J? And I know we can write in K, so let's put 0 on the K. And what units would this R be in? We want to be units, we want to put meter. Isn't displacement in meters for this problem? Okay. Somebody want to give me the displacement? Which one would be convenient? We could go to almost any point, all points. There's a lot of points, but the one that's most convenient is going to be this point of application. So let's pick that out. So what is from A to that point of application? What do I have to change in the X? Minus 3. What about the Y? Plus 2.3. And the K we already did. What about F? I have to express that as a vector. Something in the I, something in the J, something in the K, in units of Newton. What will it be for the I? 350. All right. Okay, I'm going from A to this point right there. And X will leave as positive going out that way. Okay, so everybody work out what this is and then work out what that is. And will it make a difference if this is plus or minus and that's plus or minus? Yeah, the sign is going to be very important. You have to get the sign right, right? So work it out. I'll walk around and look at it. 350 times something in the I, 350 times something in the J. So let's go ahead and do this. What we want to do is we want to pick off this component in the X and this component in the Y. And I'd focus on this right triangle because we're given this angle to be 30 degrees. And so it'll be 350 newtons, put the newtons out here, times the sine of 30 in the positive X. And then in the Y, it'll be negative 350 times the cosine of 30 degrees. All right? And then what's it going to be in the K? 0. Once I do that, I set it up, use my little memory enhancing tool, you know, mnemonic, graphically, how to do the cross product. It's really, the cross product isn't defined as a determinant of some funny matrix. It's just easily remembered that way. Okay. And then you compute it. You will get the same answer, but you'll get a vector resultant. And you'll get, what will be the answer for the component in the I? 0. How about in the J? 0. And then in the K, using right-hand rule, which way will it make it want to rotate around? It'll be a positive something Newton meter for the units. And we've solved this problem before. Don't you get it's 500 something? What is the answer? 506.8 or 507 Newton meter in the K. Positive. Good? Good. Now we get to probably where you were wanting to get to early. You're going to get to the principle of moments. There's also known as, and I don't know how to pronounce that name, Varignon's theorem. We probably butchered it over the years. Probably if the person's family was still around, they say, that's not how you pronounce the name. But anyway, what you do is if I wanted to compute it's easy to show in 2D. If I wanted to, here's point A, here's my object, here's my force right there applied. Maybe not put it aligned with an axis. Maybe put my force with some component. I would decompose it into a component in the x, f of x. Oh, come on now. F of x and f of y. All right, there's my f. And then I would take and say, what does f of y do around point A? Oh, that one's pretty easy because that distance, that perpendicular distance, is pretty easy to calculate. And then I would say, what about f of x around point A? Well, that perpendicular distance is easy to calculate. So I'd actually decompose my vector force into two forces, compute each moment individually, sum them back up, and there you go. Isn't that what the cross product's doing? Yep, it really is. Okay? So you decompose your force into components, and then compute each component's moment arm. Easy. This is probably the way most engineers would do it. Oh, they would conceptually work with that moment arm to get the sense of rotation and check things, but to actually calculate that moment arm distance in 2 and 3D a lot of times is a pain. So they would do this using the principle of moments. So, same problem. How would you calculate it? Well, if you do it with the cross product, you're going to see, aren't I just kind of speeding up the cross product? You're exactly right. So anyway, you would decompose it into this component, which is f times, what is that? The cosine of 30. And then this component, remember, they are all applied at this point, going right there. That's the f sine of 30. And then you would come down here and say, what is that moment arm distance for this one? 2.3. And what is the moment arm distance for this one coming down? 3.0. And so the moment about point A would be my f of x times the moment arm distance. I'm just going to say dx. And then I'm going to have f of y dy. And I have to worry about those signs. So let's just do this one. F of x is going that way, positive. Which way is it going to want to rotate around A? In the negative sense. And then what about the f of y coming down? Which way does it want to rotate around A? In the positive sense. So this would be my 350 newtons with the minus sign, forgot the minus sign right there, times the sine of 30, times my 2.3 meters, plus my 350 newton, times the cosine of 30, gets the down component, times my 3 meters, and you add it up and you get exactly the same. The right sign and everything. Can you see how we solve the same problem 3 ways that may look different, but give the same answer? Determine the resultant moment about the location A. So I have two forces, F of this and F of C. So F of C and F of B, because it's applied at point B and applied at point C. And we're interested in calculating the moment of those both forces around point A. What is that resultant moment? The net moment around point A. Can I give you a minute to do that? So, in the interest of time, let me try and describe this. You can work, a lot of times we like to work in the XY coordinate system, true? But you know what? There's nothing that says X has to be on the horizontal. You can work in a slanted coordinate system, X and Y, can you not? Yeah. And so look at what we can do is take this force here and we can decompose it into that component and that component. And it's applied at point B. Let me think about this one. This would be like the force F, B in the X, and this would be the force F, B in the Y. F, B in the X, does it generate any moment around point A? No, it goes right through point A, right? So the only thing that's generating a moment of this due to this 250 newtons is this component FBY. So guess what FBY is? Isn't that going to be, this is that angle right there. You get a right triangle. Right. Oh, you're going to get good at right triangles, aren't we? So this will be 150 newtons times the cosine of 25 degrees. And so if I wanted to calculate the moment of this 150 Newton force, FB, around point A, this is that moment arm distance, that perpendicular distance. So you would get 0.76 meter times 150 Newton times the cosine of 25. That would be due to the first one. That was making it want to rotate in the positive sense, so leave a positive sign out there. And then likewise for this one, we can decompose it. This is going to be a component pushing in. That's not going to contribute, but we pick up a perpendicular component, and that is going to be F of C times, there's my 90-degree right triangle. This is my 30 degrees right in there. Cosine of 30 degrees. So it'll be plus the distance. I add this one and that one. That gives me 0.98 meters times 200 Newton times the cosine of 30. Does that look good? Unit would be Newton meter. All right, let's press forward. You can take a problem like this. Here's point A. Here's where the point of this application of this force, 400 Newton force. Can you calculate the moment of A using F times D, where I have to calculate that hard to calculate parameter D? I forgot the name of D. What is D again? Moment arm distance. That's exactly right. Can you then calculate it almost seemingly like a completely different method using mathematics only? Forget you're an engineer, you just do the cross product. And the other one, principle of moments, where you decompose this into this force and this force. That one has this perpendicular distance. That component has this perpendicular distance. Can you do that? Do it, please. Not now, though. Now let's talk a little bit. This is very confusing to me when I first ran across moments of forces. I just remember this a lot. Because if you ever worked with a torque wrench, maybe a lot of you have worked with a torque wrench, you know what moment of a force is, right? It's the torque wrench. It's the same thing. Moment of force, torque, and moment are all typically thrown out and used in the same context. But torque and torque wrenches are often for machinists and mechanical engineers and tightening bolts and other things. And the more general is moment of a force. All right, well, how many people have used the torque wrench? How many people remember what's the torque on a bolt on a head? Let's say you're doing automotive work. That's my first, right? I got to look at the book. You got to torquing your head bolts down, right? Anybody had that experience? Remember what it is roughly on some of these crank bolts or the head bolts on an engine? You get so many foot-pounds of torque. Or maybe you had inch-pounds of torque. I remember, oh yeah, I need 180 of this foot-pounds of torque, or 220 foot-pounds of torque, right? And then it became ingrained. Torque are units of inch-pounds. Torque is in units of foot-pounds. But when you get to the SI, guess what the units of moments and torques are? Newton meter. What's the difference between an inch-pound and a Newton meter? Not just conversion factor, the order. What's the difference? Do you see the difference? Force, then distance, instead of distance, then force. You say that's a small thing. It threw me for a loop for a long time. Like, huh? Why isn't it meter Newton? And then I said, look it, the moment of a force is R cross F. What comes first? Distance. What comes second? Force. Why isn't it like I think it should be, foot-pounds? But it's not in SI. It is always, I'm just telling you, it's always Newton meter. And then when I saw this equation for the shorthand, m is equal to f times d. Oh, come on now. What's the big difference on the order? Why don't you put d times f? But nobody does. There's nothing special to say the book must have f times d. They could have written it d times f, which would have made me a lot, easier because d is closer to r and f is f. This was very confusing to me. All I can say is these are the units, and it may not be consistent in the way of whatever, perfect, but this is the units. And so for scalar analysis, it looks like, hey, this is, a Newton meter. That looks like the best units. Vector analysis, hey, it looks like it should be a meter Newton. Okay. And then you take a look. Anybody bought anything from this company, Granger? They have outlets all over. You can buy stuff. So I thought I'd just go on there and I'd say, all right, give me a torque wrench. I want to buy a torque wrench today. And they will have torque wrenches. Now a lot of things are digital, right? And so you just click a button and you get it in different units on digital display. But the older is like you have to specify your units and range of units. Look at the units. Foot pound, thumbs up, makes sense to me. There's a whole bunch of them in these foot pounds. I don't know why there's two sets here. But you can see that they have 174 torque wrenches. What's the next? Inch pound. A lot of inch pound, right? And maybe some people were in military application, maybe in the Air Force doing mechanic work. A lot of torque wrenches and torque specs. Did you know there's not one bolt in any of your vehicle that doesn't have a torque spec that engineers have spec'd out? Everyone, and it's definitely in something really important like military aircraft or military engines and tanks and stuff. Everything's got to be torqued. It's all very, very specified by the engineers. So anyway, here look at Newton meter. Then they have Newton centimeter. Okay, that makes sense. Meter kilogram? That's because there's a lot of slang out there, and they talk just kilograms like a unit of force, just like we talked. Right? Oh, this one, centimeter kilogram. So that's common too. So anyway, you can look at on the internet, you can look at different, like here's a gauge, it's showing you inch pounds on one side and Newton meters on the other. And here's one Newton meter. Here's one, it's an old one, foot pound. All right. We have enough time. We need to jump into section 4.5. Oh. We have been talking about calculating the moment of a force about a particular point. And then even in 3D, especially if you do 3D, you get this C or M is R cross F. But that's a vector, isn't it? Yeah. And so about a point, you can get a vector for the moment of that force that generates on that body. Often we're not interested in it. We're interested only in along a particular axis that goes through that point O. Maybe we have a wrench on the bolt head and the threads are this way and we're trying to turn the bolt. You may be putting a moment on that bolt which isn't completely aligned with the axis of that bolt. And the way they generate or display moments in this textbook is they'll put it like a force vector with a little arrow going around. Okay? So this is how they represent a moment. And what you want is you don't want it, you want it at the head of the bolt. Yeah, that's point O, but we want only the component along a specified axis. This is very common. But mathematically, people are like, what? I'm getting confused, Professor. Relax. It's not that hard. Because once you get the moment at that point, then what you can do is just get the projection of that moment, treated like a vector, what it is, in the direction of interest. And how do we characterize the direction of interest? A little unit vector. And now we have to make up a new subscript. And so, oh man, we've used a lot of uppercase letters. We've used a lot of numbers. We'll go to lowercase letter a. So what is the lowercase letter a? It's for this axis of interest going through point O. So if you wanted to get that magnitude of the component, maybe I drop back to a dot product. If I did MO as a vector, dotted with U, A, the unit vector defining that axis, then I'll get the magnitude of that moment around the axis, which will actually do the usefulness of turning that bolt. It'll do that's what I'm interested in. So mathematically, it doesn't matter if you do the dot product first or second, so u sub a dot. So this is what happens. So you calculate u sub a, somehow you get the unit vector. You dot product with that moment. How do I calculate the moment of some force about, isn't that r cross f? So first you do r cross f, you get the moment, and then you do the dot product. So when you have the cross and the dot like this, guess what they call that? Not the double, the triple. Because there's three things doing some multiplication, so it's a triple product. So that's how you get the magnitude of m sub a. If you want to re-express it as a vector, just multiply back by u sub a, and you have a vector for that moment in that interesting axis A. All right, so what is the triple scalar product? Well, if I had a vector A, I could dot it with another vector, but that vector could come from B cross C. And so this would be a triple scalar product. Can the triple scalar product produce a negative result? Yes or no? It can produce a negative result. And when does it produce a negative result? Maybe you think of this as another vector D, and then if I had A like this going in that direction, and I had D going in that direction, D, can you tell me a little bit about the angle theta between them? Larger than 90? And then we have the dot product of those two vectors. Would it give me a positive or negative result? Negative. Negative result. So, all right. Professor, I come to UTSA to not be a mathematician. I came here to be an engineer. Well, unfortunately, mathematics is the language of engineers. So, okay. I don't think we have time for this problem. I was going to set it up and solve it. I'll have to pick up there next time. Thank you for your attention.